today we are going to talk about line integral and green theorem. But before I start talking about line integral, I have to get some review about integral. We have integral of one variable function like this from a to b, this definite integral for one variable function. And also we have double integral over region for two function, okay, two variable function. And we end up with triple integral for a function of three variable, and we have what we call this one. This is length element. This is length element. This is, we call it what? Yes, area element. We know the area element could be what? Could be dx dy or dy dx. Okay, or could be in a polar coordinate, could be r dr d theta, if you remember. Okay, and this part we call it what? Volume element. This volume element could be in a Cartesian, could be dx dy dz, or could be in cylindrical, could be yes r dr d theta, r dr d theta dz, or could be in a spherical coordinate. This is in cylindrical, and this is in spherical. In the spherical, dv is rho square sine theta sine phi, sorry, sine phi d rho d phi d theta. Okay, as we remember from math too. I just give you a shape of this one. This is a volume element in cylindrical coordinate, and in Cartesian coordinate, and in spherical coordinate, and the area element in rectangular coordinate or Cartesian coordinate, dx dy, and in polar coordinate, r dr d theta. This is the area element and the volume element. Fine. Now we have some application, and we know this one give us what? Yes, the one variable integration function give you the area under the curve. When you have area under the curve and you're integrating from a to b, this is the area is exactly giving you by this integration, right? And this is your f of x. And we know this one, okay? And also we can find the volume by revolving the curve about x-axis or y-axis using the one variable function, right? Okay. Fine. And also we can find the surface area and etc. Double integral straightforward give you the volume, right? Because when you have a height times the base area, give you the volume. But if you have this one equal to 1, the double integral give you what? Give you the area, right? Also, in this case, I don't know, you can have what by the triple integral, but if you have this one equal to 1, it give you the volume straightforward because you are going to integrate the volume element, and here you are going to integrate the area element, right? This is all the integration we know from Math 2. So what we are going to do today, yes, we are going to go for line integral, and we link this line integral with double integral first and then by triple integral. Okay, so we will link the double integral with the line integral by Green theorem in 2 dimension, and we link it to the triple integral by Green theorem in 3 dimension. Let's go first by the line integral. We have 2 types of line integral. Okay, we have a line integral when you have a scalar function, so you will have this notation, and in here you know you're integrating over interval or segment. Here you're integrating over area. Here you're integrating over volume, right? In the line integral, you integrating over a curve C. And the direction of the curve is very important, okay? If you go anti-clockwise or with clockwise. Anti-clockwise, it will be positive. With the clockwise will be negative, right? Okay, so this line integral over the curve C for 2 variable function, x and y. And here you have this arc length element, you can say. Okay, fine. So this is exactly line integral in this case will be very similar to the definite integral in one variable function, right? So what? Yes, you have your C, and if you have the parametric equation of your curve as a function of the parameter t and y as a function of the parameter t, so you can replace everything here by in terms of t. Okay, what about ds? As I said, ds is the arc length. What is the arc length? Yes, I remember when I got this one, I have an application for the arc length. Arc length L was what? Yes, integration from A to B for 1 plus dy by dx square dx, or if I have parametric, this L will be what? Integration from A to B for, yes, dx by dt square plus dy plus dy by dt square dt. This is the arc length when you have a parametric equation. This is when you have Cartesian equation, a Cartesian function. Okay. Now, what is ds? Yes, I just said the arc length is this one. Once you have a parametric, so you replace this one by root square. Yes, root square of dx by dt, and you square it, plus dy by dt and square it, and integrate with respect to your parameter t. Okay, this is the line integral in 2 dimensions. In 2 dimension, right? What about if I have 3 dimension? Okay, if you have 3 dimension, it will be exactly the same, integrating over C, okay, for a function of 3 variable. Excellent, yes, because you have 3 dimension. And you have also ds. ds in the 3 dimension will not be the same as 2 dimension. It will be extra dimension. So this will be exactly like integrating from a to b over the c. Yes, you replace each x by the parameter t, so this will be a function of t, right? It will be a function of t. Sometimes they call C, if they write C as a term of position vector, as x of t in the direction of x, y of t in the direction of j, so you can work out this one as f r of t if you are in 3 dimension. Okay. And what is ds? Yes, ds very similar to this one, but in this case I can write it x dot square plus y dot square plus z dot square dt. And I know x dot is a derivative with respect to t. X dot is dx by dt. Y dot is dy. Because I don't have enough space, so I can write it like this. Z dot is dz by dt. That's it. This is a line integral, okay, in 2 dimension and 3 dimension. Let's have an example. Let's have an example. Evaluate the line integral over a curve C for the function 2 plus x squared y ds, where C is what? Is the upper, yes, is the upper half of the integral. The upper half, sorry, of the unit vector x squared plus y squared equal to 1. Okay. Now I have to sketch C, and I have to get the parametric equation of this C. Otherwise, I cannot find the line integral, right? Okay. So first of all, I have to graph C, have the parametric equation of C, okay, and then get the arc length, right? dx by dt and dy by dt, and square both of them, add them together under the root square, and then add it in this formula. Let's do it. Let's do it. First of all, the upper half of the unit square. Let's, okay, this is the upper half of unit square. So I have -1, +1, and I have here +1. I have only the upper half, so I got this one. Now, this is the upper half, and I have this one, x squared plus y squared equal to 1. Because it is the upper half, so I get y bigger than 0 or equal to 0. So this is the upper half. So this is my C. This is my C. I graph this one. How I transfer this one into parametric equation? I know the parametric equation for the circle with radius A is A cosine T or theta. Theta or T is the same parameter. and y equal to a sine t. A here is 1, right? A is 1, so I end up with cosine t for x and sine t for y. I would like to have dx by dt, which will be minus sine t dy by dt is cosine t, square both of them, dx by dt square plus dy by dt square, and put it under the root square, will equal to what? Yes, it will be equal to sine, sine square t plus cosine square t. So I know sine square plus cosine square is 1. This is 1. So I end up with 1. Now I parameterize my C. I find this ds. Okay, a part of ds. Now to evaluate from over this one, my function was what? 2 plus x square y. 2 plus x square y. 2 plus x square y ds. Now I replace x by cosine t, and I'm going to integrate from what? T from where? Yes, t, because I have the upper half. If you have t at the theta, so you start from 0 to pi. So t from 0 to t equal to pi. So I'm going to integrate from, yes, t from 0 to pi. Okay, 0 to pi. Yes, 2 plus x is what? Cosine t. It is x squared, so I have cosine square, times y. Y is sine t. I have root square. This root square is 1. Okay, so I have 1 dt. Do you have your calculator? Can you do this one in your calculator, please? I can do it without calculator, by the way. The integration of t is 2t, and by substitution, I have cosine as u, so du will be minus sine. So in this case, I have the integration is equal to minus cosine cube t over 3, okay, from 0 to pi, and substitute. Okay, did you have it by the calculator?
Yes, doctor, but this take time.
Sorry?
6.36.
2 pi plus 2 over 3. Okay, this is a value in a proper way, because when you have t equal to pi, you have 2 pi. Okay, when you have 0, this will be 0, and this 2 over 3 will coming from the cosine pi is equal to, this is a cosine. Okay, cosine start from 0, it will be 1, add pi over 2 is 0, add pi equal to minus 1, right? Okay, so, and also add 0, it will be 1, so I have 1 minus minus 1, it will be plus 2 over 3, so it will have 2 over 3. Easy? Okay. We finished this example. Let's have another one in 3 dimension, please. Evaluate the integration of the function is y sine z ds. What's c? C is a helix given by x equal to cosine t and y is equal to sine t and z equal to t. This is the helix. Helix is like that. When you go helix like that. Okay. Yes, this is in 3 dimension. I'll follow the same thing, right? What I'm going to do to solve the line integral. First of all, I graph it. It's okay if I graph it or not. In this case, I don't mind. So I will have dx by dt, which is minus sine t, and I will have dy by dt. dy by dt is cosine t, and I have dz by dt equal to 1. Now I will have root square of dx by dt square plus dy by dt square plus dz by dt square. So I will have what? I will have sine square t plus cosine square t plus 1. I know sine square plus cosine square is 1, and I have another one here, so I end up with root square 2. Okay, now I'll go and do my line integral. The integration of y sine z ds will equal to the integration. Yes, he didn't mention t here. T from 0 to 2 pi. Okay, so from 0 to 2 pi. What's y? Y is given here, sine t. What is and sine? What is z? It's also t. And I have ds is root square 2 dt. Now I have sine square. I can get this one outside the integration. It is a constant. And I have the integration of sine square t dt. I can use the trigonometric identity, and this is half 1 minus cosine 2t dt. Sorry. Half 1 minus cosine 2t dt. You can integrate, or you can use your calculator to do it. So this is over 2. This integration of 1, I take the half outside, is t. The integration of cosine is sine 2t over 2, and you substitute from 0 to 2 pi, and you end up with root square 2 pi. Easy? Fine. This is the line integral in 2 dimension, 3 dimension with a scalar function. Okay. What's next? What about the vector? Because we are studying vector calculus. Okay. So I go for the line integral of vector field. Yes, you have to integrate over a curve given by the parametric equation if you are in 3 dimension, you will have x, y, z. Okay. So, and what? Yes, the integration over this curve will be the line integral over the vector field for the vector field F. Like force, like magnetic field, okay? F dot dr. So this will be exactly like what we have done before. Yes, will be the integration, definite integral. It will be transferred into definite integral from a to b over the c. For, yes, I replace x and y, z in my vector field by the parametric value. And yes, you have r dash of t dt, right? Okay. Some people would like to have this one as integration, and they consider this one with the tangent of the c at the point x, y, and z. I would like to, I prefer this formula, right? So what you need c in the parametric equation like this one, and you have to differentiate this one, okay? And you have to know from where you are going to go over the c, right? Okay. Let's go to our presentation to have an example for this one. We have done this one and also this one. Now we know the work done by a variable force f of x in moving a particle from A to B along the x-axis is the definite integral, and this is also one of the applications. What about over moving a particle along a smooth curve C? Okay. Yes, you have this formula. As I told you, this is the tangent at the point x, y, and z for the curve C. Okay. Once you substitute the tangent as the derivative of the position vector over the magnitude of this vector, give you the unit vector in the direction, in this direction, right? Now you end up with f dot gr will be exactly the definite integral from a to b for f after replacing x, y, z by the parametric values, and you differentiate your c with respect to the parameter t, and then you integrate up to the distance you are moving over the c. And remember, when you're moving anti-clockwise, will be positive, and with the clockwise will be negative. Okay. This is the example. Find the work done by the force field fxy equal. So you are in 2 dimension. He gave you the c in the parametric as a vector, and he give you the boundary of the parameter, right? As I said, first of all, yes, you have to replace in your vector field x, y, z in the parametric values, okay? And then you differentiate your c with respect to the parameter. Now you go for the work formula in the line integral of vector field. It will be transferred into definite integral with the boundary of the parameter for your vector field after replacing x, y, and if you have z by the parametric values, and you differentiate the c. Okay, so yes, this is the things after you substitute. This is very simple integration. So you can do it by the calculator, you can do it by hand. Now we will go for our mission for today. This is a green theorem. What's green theorem doing? Green theorem will link the line integral with the double integral, right? Okay, this is the main point of, and this integration you can find it in something called flux, if you heard about the flux of a vector field. Okay, so you link the divergence of the field over the interior of the region, okay, by using the double integral of this divergence, right? Okay. This is what we are going to do, and we know the curl measure what? Measure the float rate of rotation at each point. And the divergence of fluid velocity field measures the rate of which fluid is being piped into or out of the region at any given point. This is what we know about the curl and the divergence. What's the Green theorem formula? The Green theorem formula, as we said, you are going to integrate over any curve, smooth curve. So you have the line integral. This is f dot dr. Why it's f dot dr? I'm just explaining to you. Dr, fr in this one, fr is xi plus yj. So dr will be, yes, dxi plus dyj. If I have f equal to, I have two components, okay, f1i plus f2j. Okay, so if you multiply, dot product of f dr is exactly f1 I plus f2 j dot, yes, dxi plus dyj. When you multiply by dot, I dot I is 1, j dot j is 1, but I dot j is 0 and j dot I is, so you have what? f1 dx plus f2 dy. So I explained to you why f dot dr is equal to this one, right? So this is f dr. So this line integral give you the work over the closed smooth curve C will be changed into double integral. The one in front of dy you differentiated with respect to x minus the one in front of dx you differentiated with respect to y. So yes, I can find the double integral using the line integral or the line integral using the double integral. Okay. Some people using this formula, instead of f1 and f2, they call it pi plus qj. So this is the same thing. Instead of F1 and F2, they call it P and Q, right? The green theorem formula, F dot dr is yes. This is coming from what? From the determinant of the curl, right? This is why you have this formula as a curl. Okay, so you can write it. Why does k, the unit vector in the z-axis direction, appear in this double integral? Can you explain to me why k? Okay, I will leave it for you. Now I would like to have the work or the line integral xy dx plus x squared y cubed dy, and the c is this triangle, right triangle. Okay, so I don't like to have this one because I don't have the parametric equation of this triangle, right? Okay, so it is easy to transfer this one using Green theorem into double integral. So the one in front of dy, you differentiate with respect to x, minus the things in front of dx differentiated with respect to y, and have the double integral over your c. Okay. And you have to find the boundary because the double integral need the boundary of x and the boundary of y. How to find the boundary of x? Why he get x from 0 to 1? Yes, I have x from 0 to 1 because he give me the 3 points as a vertices of the triangle. How I get y from 0 to 2x? Yes, to get the boundary of x, you come from the left to right horizontally. So first you will hit the 0 and then you end up with y. If you go for y, okay, you hit x axis, which is y equal to 0, and then coming to the end with this line. This line equation, how I get y equal to 2x? I have this point 0 and 0, and I have this point 1 and 2, so I can find the slope, and the y-intercept is 0, so y equal to mx plus c. C is 0, the y-intercept is 0, and the slope is the difference of y over the difference of x. The difference of y here is 2 minus 2 over 1, because the difference of y is 2 and the difference of x is 1, or the opposite over the adjacent for this angle with the x-axis. This is the same as a slope, right? So I have this hypotenuse equation as y equal to 2x. Fine. So I will integrate with respect to y first, right? As I know in the previous math course. Okay. So I integrate with respect to y first from 0 to 2x. After I end up, yes, remember when you're integrating with respect to y, you consider x as a constant, right? So here y cube will be integrated only and x will be stay as it is. And this one x nothing, so I'm integrating with respect to y, so x is constant and the integration of dy is 1. I substitute by 2x for y and absolute substitute 0 for y because I integrated with respect to y. After I finish, I can use my calculator or I can integrate again. X to the power 5 integration is x to the power 6 over 6, right? And the integration of x squared is x cubed over 3. So it is easy to have the line integral by the double integral. Okay, but the main point of the double integral, you have to know which one you are integrating with respect to u first. This is why I told you about the area element for the double integral, dy dx or dx dy. If I would like to start from dx dy instead of dy by dx, it's easy because x will be equal to what? Half y. And I make dx first. And y will change from 0 into 2. So you can do it by dx dy, and you get, if you get the same result, your work will be okay. Okay, this is the Green theorem. This is another example. He would like to have the line integral for this one over the c. What is the c? It is a circle of radius 2 centered at the region at the origin, sorry. Okay, so yes, I can do this one as a line integral because I know the parametric equation of the circle with radius 2. It is 2 cosine t as x and y is 2 sine t. And t from what? 0 to 2 pi. So I can find the line integral. But if I would like to use the Green theorem to change this one into a double integral, remember, once you have a circle, you go for the polar coordinate. Yes. If you use the other formula, instead of F1 and F2, you use P and Q. So this line integral will equal to what? What in front of y? You differentiate it with respect to x, so it's minus 3x squared. Minus, this minus is in the formula, right? What is in front of x with differentiated with respect to y, so you have minus 3y squared. Now this area element is what? Yes, this area element, because I have a cylinder, circle, so I can change everything into the polar coordinate. In the polar coordinate, I know x is r cosine theta, okay, and y equal to r sine theta, right? So I can get this one. And the area element is r d theta. This is why you have r cubed. X squared plus y squared is r squared. But in the area element, you have r d theta. So r times r squared will be r cubed. And also, r changed from 0 to the radius of the circle, and theta will change from 0 to 2 pi because you go over the whole circle, right? Easy? If you have this line integral and you have C, yes, you have two circles in this case. One with radius 2 and the other one with radius 1. So you have like a ring, right? Yes, you have like a ring. And remember, if you go outside, you go anti-clockwise. If inside will be with clockwise. So remember, integrating over C1 will be positive, integrating over C2 will be negative. Yes. But I'm not going for line integral to put this in my mind, positive and negative. I will change this line integral into double integral to get rid of the positivity and negativity of the direction. Okay. So yes, what in front of y differentiated with respect to x, so I have minus 3x squared minus from the formula the derivative of what in front of x with respect to y, so you have minus 3y squared. This is why you get minus 3 as a common factor. Okay. Now, once I see the circle or ring, I go for the polar coordinate. In the polar coordinate, x is equal to r cosine theta and y equal to r sine theta, and the area element is r d theta. So I have r squared from this one, and I have r in the area element, so it will be r cubed dr d theta. And remember, the radius here for the ring, starting from inside to outside. The inside one with the radius 1, the outside one with radius 2, so your radius will change from 1 to 2. And because you go for the whole circle, you go from 0 to 2. It's very simple integration. R cube integration is r to the power 4 over 4, and you substitute by the upper bound r equal to 2 minus the substitution of the lower bound r equal to 1. So you end up with this one. Now the integration of d theta theta, you substitute by theta equal to 2 pi minus the substitution of 0, so you end up with 45 pi. Okay. There are some application of Green theorem because you go for double integral, and we said the double integral, if you have the function equal to 1, you are only integrating the area element. So once you integrating the area element, you have the area, right? So we can use the line integral in finding the area, right? So you may have it as x dy, the line integral of x dy, or the line integral of minus y dx. I would like to use both of them. So if I add this two together, I'll have double of the area. So the area will be half of the addition of this two formula. Okay, this is the area element This is the area using the line integral. And I was expecting this one because the line integral is exactly like what? If you remember here, is you end up with this one as a line, as a definite integral, right? In the beginning, we have as a definite integral. So I was expecting the definite integral of one variable function is an area. So I was expecting Green theorem to give me the area. Okay. This is the example to find or to prove the area of the disk with radius a is pi a square. So this is the formula I got from the line integral. As for the area is half x dy. For the disk, x is cosine a cosine t, and y is a sine t, and t from 0 to 2 pi. Yes, I will have the area similar to what I memorize in my mind by a square. If you have a cardioid like this one, right, and you would like to find the area of this cardioid, you will use the formula of the area in the polar coordinate. The area element, the area in the polar using the line integral is half the integration of r squared dθ. Okay, so you have to distinguish between finding the area in the Cartesian like this one. The formula using the line integral is half the integration of x dy minus y dx, but in the polar you have half the line integral over the curve given in the polar coordinate r squared dθ. Now this is your turn. This is the exercise. I'll stop recording now and I'll ask you to find this one using the line integral and change it into double integral using Green theorem, and you find the two answers and must be the same answer, right? And if you have any question, please ask.